Hello everybody. From chapter 2, section 2, I did not do example 6 where we were talking about higher derivatives. If you look at this notation here, that means the second derivative, not the first. That also means the second derivative. This means the second derivative. This means the second derivative. Oftentimes, these ones at this level are used the most. I don't think we'll be using this one at all in our class. Not only do we have second derivatives, but we also have third derivatives, fourth derivatives, any derivative you want. So if you remember, I skipped this problem in class. It was somewhat long. I'm going to go through it quickly here. But if we have a function, we have to take the derivative of this to get the first derivative, then take the derivative of that to find the second derivative, and take the derivative again to find the third derivative. So let's go ahead with this. So if you remember from example 1 in the first part of section 2.2, we did this problem and got the first derivative to be 3x squared minus 3. So we're going to borrow that so we don't have to do that all over again. And to find the second derivative of that, now I want to throw in some new notation here for you. This can also mean, or does mean, take the derivative of the derivative, which is the second derivative. So we're going to use our good old limit law here. So notice we're using the definition of our derivative, but instead, since we're looking for the second derivative, instead of plugging in f of x, we're plugging in f prime of x, which brings us to here. Go ahead and distributing, we'd get to here. Pause your video at any time if you need to work this out. And you'll notice we're in the situation where we can factor out our h's and we can cancel them. And 1 second, please. I just noticed a very silly mistake here. So sorry, but there should be an x by the 6. So sorry about that. X, there we go. And then that will give us 6x, which equals the second derivative. So if we now want to find the third derivative, that means we have to take the derivative of the second derivative. So you're probably seeing why I didn't want to throw this in at the end of class the other day. All right, so here we have the third derivative equaling 6. Last one I skipped from the other day was, I believe, the last one in this packet. I believe we went over this a little bit. Velocity is the derivative of position. Acceleration is the derivative of velocity, which means it's the second derivative of position. Our jolt is the derivative of the acceleration, which is also the second derivative of the velocity, third derivative of the position. That's important, okay? We're going to be using that a lot in the future. Okay, so we're looking at this graph below, and we try to say, which is the graph of f, f prime, f double prime, f triple prime. In other words, which is the graph of the position, the velocity, the acceleration, and the jolt. Please remember, when the derivative is 0, that means the function has a horizontal tangent. So it might take you a little while to play with this, but take a moment and look at the graphs A and B. If you notice A has an x-intercept right here and about right there-ish. And if you also notice, when that happens, doesn't B have a horizontal tangent at that point? So this tells us, begins to tell us, that A might be the derivative of B. Okay? You might also want to remember if the derivative is positive, then that means its function is increasing, and you can check for that. You can also remember if the derivative is negative, B is decreasing. Okay, moving on. Now, if we take a look at A, let's look where A has a horizontal tangent. And if you notice, there are no x-intercepts here, which means A has no derivative. So what that means is our A has to be our third derivative, or our jerk. And if A is the derivative of B, that means B is going to be our second derivative, or our acceleration. Let us examine B carefully, and let us take a look. Let's see what else is remaining. Let's take a look at C as well. So now we're going to take a look at B, and we're going to take a look at C. When you play with this for a little while, you will notice that where C has a horizontal tangent, that is indeed the x-intercept of B. So that means B is the derivative of C. Which means C is the first derivative, which is our velocity, which leaves us as D as our position function. And we can call that S of t. Usually position is S. Okay, that was a tricky one. Hope that helped.